Alright everybody, we're back with part 2 of our pneumatic joint project for the Stellar Robotics 2018 CAD class. If you remember from the last video, we created this layout sketch. Now we're ready to start modeling some of the structure and getting parts in here. Some of this is a little bit difficult to explain exactly what we're going to do, so I'm going to leave some of that explanation until the end of the project once all the parts are present and I can kind of point to stuff and explain the reasons why we're doing stuff. The particular way that we are. However, I will do my best to explain up front as much as I can, and then just note that everything will be a lot clearer once it's complete. So obviously we need something to mount all of this to. It's kind of like a base plate. We mentioned earlier that we're going to use a piece of 1x1 aluminum tubing, which is a fairly common piece of structural aluminum that's used in FRC. And then this here represents the pivot point of the mechanism. This here represents the pivot point of the air cylinder, the back end of the air cylinder. So we're going to have some brackets that attach to the sides of this tubing that come up and have holes in them that allow us to put pins through and mount stuff that way. So let's start with this piece of tubing. So I want the tubing to be this length of this line plus an inch on this side and an inch on that side. Once again, normally this piece of tubing would be some other part of your robot. You wouldn't normally have an extra piece of tubing here unless you need it for something. So I'm just giving myself an inch on either end just for the sake of this project. However, in your application, whatever you're attaching this mechanism to will be what it is on your robot. So let's use the measure tool. I'm going to press the M key. I'm going to click this line. So I get 11.189 inches. So that's kind of a weird number. It's not fractional. It just has to do with all of the weird angles we have involved. But that's okay. We're gonna leave it that number, 11.189, and we're gonna add an inch on either side of that. So it'll be 13.189. So I'm gonna create a new part here. This will be a standard.ipt. I'm gonna click create. All right, so I'm going to model the profile of the square tubing. So I'm going to start with a rectangle, and it's going to be 1 inch, and press tab, 1 inch, press enter. Okay, so we have a 1 inch by 1 inch square. Then I'm going to press escape, and I'm going to use the offset tool right here to create a second rectangle offset to the inside. Now we're going to use 1/16 of an inch wall tubing because that's pretty much all we use on Stellar Robotics. We got a ton of it laying around, so that's what we use. So 1/16 is 0.0625, or you could type in 1 divided by 16 if you're more comfortable with that, and then press enter. Alright, so this is all with this sketch, so we're going to finish the sketch. We're going to use the extrude tool. So click the outer region there. It was 13.189 was the length. Some of these dimensions, if you can remember them, great. If you can't, make sure you write them down so you don't get them wrong. You absolutely don't want to be, when you're transferring dimensions like this, where I just went in and measured it in a layout sketch and then came to a part and modeled it, which is typically how you're going to do it. You need to make sure you get it right. So write this stuff down if you have to. So we're gonna use this third option here, symmetric, so that it extrudes it evenly on either side. That's just a good practice to get into when you're extruding long things like this, is to just make them symmetric. I'm not going to go into the reasons for that here, but that's just a good practice. So click OK. Click the drop down. We're going to select the material. This particular tubing is not actually 6061, but I'm not particularly worried about the very, very small density differences between 6061 and 6063 in the case of this tubing here. So I'm going to save this. We're going to call this part 1. Like that. Alright, that's all we're going to do for now. We're going to go through and we're going to get all the brackets on here, then we're going to add all the mounting holes and everything later. So mounting holes are typically the last thing I do. In our gearbox project, we didn't really have an opportunity to demonstrate that very well. Close out these. Just because the mounting holes were fairly integral to the structure and we had to model them up front. But typically when we're working with sheet metal and tubing like this, we're going to be using we're going to be doing a lot of modeling first and then adding mounting holes later. Okay, so next we're going to come back to this pivot point here in a second. Let's get let's get this air cylinder in here. The air cylinder bracket anyways. I gotta, yeah, so we're gonna model this bracket first. So, alright, so let's look at the air cylinder here. So we've got, I'm gonna measure the outer diameter. Yeah, so the outer diameter of this air cylinder is larger than the width of this tubing, right? So the air cylinder is wider than this tubing. So if we've got a bracket on this side and a bracket on this side that's just flat plate aluminum, oops, bumped my mic. Okay. The air cylinder won't be able to fit in between those two plates. So essentially what we have to do is we have to have a bracket. If I look at the top of this, we're going to have a bracket here, and we're going to have a bracket here, and they will hit the cylinder here, and there's actually going to be a fitting here, so that's another thing to consider. Basically, they've got to reside in this region while still having a hole in them to allow a pin to go through. So let's measure the distance from the center line of this axis here to the back face of the cylinder, 0.34. Okay, so we want to be just under that to make sure that we have enough room for this air cylinder to pivot up and down. And once again, this will make a lot more sense when you can actually see the air cylinder in an assembly. So I'm going to go ahead and start modeling the part, and if you don't quite understand what we're doing, it will make a lot more sense once it's in an assembly. So follow along and all will be made clear. So we added an inch on either end of this. So if we go back to our layout sketch, we know that this tube is an inch longer than the layout sketch line is on either end. So basically my point is the pivot point of the cylinder will be an inch in from the end of the tube and 2 inches up from the top of the tube. So, and then we're going to kind of make this like kind of an L shape, so that we've got some, we're going to put rivet holes in the sides, because normally we would rivet this assembly together. So let's create a new part here. I did that using Control N, click standard.ipt, and click create. Typically this is going to be a flat bracket that's probably 1/8 of an inch thick. Typically for those I don't use sheet metal, but you can do it either way. All right, let's let this center point here represent the pivot point of the air cylinder. So let's go back to the air cylinder model here. We want to know what diameter hole this is. So I'm going to use the measure tool by pressing M, click the circle, so it says 1/4 inch. Okay, so what we're going to do is we're going to create a circle that's 1/4 inch diameter. Now actually we're going to add a little bit to it, because normally when you have a pin, you want it to be, you want to be able to get it through there. Now in this case, I think we're going to use a bolt or a screw. So we only want a few thousandths of clearance, so it's still relatively tight. So we're going to do 0.25, and then we're going to add another 5 thousandths to make sure the hole is large enough that the screw will be able to go through there. So I'm going to press enter. Okay, so now we know I'm going to create a circle here, a construction circle, with a radius of 0.34, and I got to do ×2 because it's actually diameter. So this represents, if the air cylinder, if this is the pivot of the air cylinder, this circle represents the closest point that the air cylinder will be at any angle around this hole. Okay, so we want to make sure that where the air cylinder is going to be, which is going to be kind of here at this angle, and it's gonna move up and then come back down as it follows this arc, right? So the air cylinder is going to be changing in angle slightly as it extends and retracts. So basically, we're going to need a slight arc here to account for that, and then in addition to that, we're going to need we're going to need some other things too. So let's start at the bottom. So if we go put a line, that looks about right. Oops. I'm going to turn off construction geometry on that. And I actually want to turn off construction geometry permanently. All right, so this is going to represent the bottom of the bracket that will be flush with the bottom of this tube. Okay, so then we're going to have some geometry that's at the back of the tube, right? And so this line will be flush to the back of the tube. Now we know from our layout sketch, what I said earlier is that the center point is an inch in from the back of the tube. So we know this will line up with the back of the tube, and this is the center point. So we're going to go ahead and dimension that. That'll be an inch. Okay. Next, some part of this is going to be flush with the top of the tube, and I said we're going to kind of make the bracket L-shaped just for structural rigidity. So I'm gonna create a line here. This is going to represent a portion of the bracket that's going to be flush with the top of the tube. This is going to be kind of the leg of the L, right? So we know that the tube, so this will be flush with the top of the tube. This will be flush with the bottom of the tube. The tube is an inch high, so we're going to dimension these two lines to be an inch apart. Okay, and we know that this hole, the center line of this hole here, will be the center line of the cylinder. It will be 2 inches above the top of the tube. So we're going to dimension from this line to the center point of the hole. We're going to make that 2 inches. Okay. We also know that we're going to have the bracket will have to end somewhere, so we're going to create another line here. We want that line to be perpendicular to one of these two. Okay, and we'll figure this out later. Actually, no, we'll do it now. So we're going to dimension this to be like 3 inches long, probably. It doesn't need to be a big L, but we do want some. So next, let's look at this. So this is the lowest angle the cylinder is going to achieve. Okay, it's going to rotate up as it comes around this arc and then back down, right? So this angle here represents the lowest point, the lowest angle the cylinder is going to be. So let's figure out what angle this is using the measure tool. I'm going to click one line and then the other, and then we find angle, which is 7.73 degrees. All right, so as you can see, if we look at the cylinder assembly, let's kind of put it in at an angle. So this cylinder here, the way we're looking at it now, is kind of the angle that it's going to mount in this layout sketch, right? So if you can imagine the cylinders right here, here's the cylinder. So we've got this like square surface here that we need to make sure that our bracket never interferes with it. So as the cylinder was going to rotate up slightly from this, but it's not going to rotate down from this angle. So we've got our hole. We're going to need some sort of curved surface in here to allow the cylinder to rotate without hitting the bracket. So we can't have any like sharp corners that would catch. However, we don't need to go straight down with the end of the bracket because this cylinder is at an angle. So we can allow the end of the bracket to kind of kick out at an angle. And the reason that that's a good thing is it provides bracing, right? Because the cylinder is going to be pushing with a considerable amount of force. So this back bracket needs to be able to take the load. So if we kind of put an angle on the front face of this bracket before it connects down to the L portion, that'll add quite a bit of structural rigidity without adding a lot of weight. So let's go back to our part here, and let's draw an angled line. So this line here represents the front face of the bracket. Now we know the angle, we know this is going to be perpendicular to the air cylinder. This line here is perpendicular to horizontal. So if we know the air cylinder is 7.73 degrees above horizontal, we know that this line will be perpendicular to the back of the air cylinder in its lowest point. This is a little tough to explain, but essentially I'm trying to think, are they complementary angles? No, I don't remember the term off the top of my head, but anyways, basically the angle between a vertical line and this line will be the same as the angle between a horizontal line and the center line of the cylinder. Okay, so basically my point is if we attach a angular dimension between these two lines, the angle between these two lines will be 7.73 degrees, which was quite a bit more vertical than I drew it. All right, so remember this circle here represents the closest point of the back of the cylinder. So if that little like nub here that has the hole in it, the back of the cylinder will be here in its lowest point. So we can get real close to the edge of this circle like this, right now, the fact that we're sticking outside of the circle below this line is fine because the cylinder will only go to here. It won't go any lower. You know, it won't come back over and interfere like we just talked about. So, but we do want a bit of an arc here to handle the cylinder when the cylinder kind of kicks up as it goes over the top of this arc. It's not a very significant angle change, so we don't need a large arc. But let's go ahead and put a fairly large arc in there just so it's visible. So we're gonna pick a center point arc. We're gonna click the center point. We're gonna click the end point of this line, and we're just gonna bring it up and around like 60 degrees or something. So I'm gonna press Escape to get out of that. So we don't have the diameter of this defined yet, or I should say the radius, and we also don't have a tangent constraint between these two, which I think is what we want. It'll look better. So let's pick a tangent constraint, click on the arc, click on the line. All right, so now we got to set this diameter. Now, ideally, or this radius. Ideally, we want this to be as large as possible. The larger it is, the stronger it is, but we really do want a bit of a gap between the back of the air cylinder, which will be here, and this bracket, just in case you know, there's any burrs on this or something gets caught in there or something. So let's dimension this arc's radius. This is pretty close to 5/16, so I think we'll just use 5/16, which will be 0.3125, or 5 divided by 16 if you want to type in the fraction. You could make this any number you wanted. I mean, you could do something else, but it just has to be less than 0.34, which is the radius of this circle. All right, so now we've got to figure out how to handle the back portion of this bracket. Now we could bring this arc around and bring a line back down, okay? But that doesn't leave a ton of material back here to act as support. However, I don't think we want to go up any higher. We really don't need to. That would just add weight that's not going to really add any structural strength to the part. We could go straight across the top, but I think this material back in this kind of corner area would be completely unnecessary, wouldn't be adding any strength. So what we're going to do is we're going to do something kind of halfway in between. We're going to bring a straight edge up the back, and we're going to kind of angle over and connect to this arc somewhere around here. The reason for that is just that's what feels right to me. You could do an analysis on this to actually determine what's stronger, what's strong enough, and likely any one of those scenarios would be strong enough. However, in an FRC build season, there's typically not enough time to do a lot of actual structural analysis. So you've kind of got to get used to designing parts as you're comfortable with while still keeping them light. And it's not an exact science, and you kind of get used to it. And if there's something really, really critical that you feel like you need to do some analysis with, you absolutely can for really important stuff. You just can't do it for everything typically. So, all right, we're going to place a tangent constraint between this arc and this line, and then I think I'm just going to assign this line an angle between here and here. We'll go, I don't know, 30 degrees. That looks fine to me. Okay, so you can also set this to be something else if you want. Maybe you don't need as large of a leg on this as is represented here. Typically, you want at least 3 rivet holes. You want 3 rivets in each part. In a part like this, it's going to have a decent amount of load on it. I would want at least 4, and 3 inches should give us 5, I believe. I might have that wrong, but anyways, we'll have plenty. So we're going to add a fillet here a little bit later to kind of get rid of this sharp corner, which will act as a stress riser, and the aluminum could tear under high loads, but we're going to add that fillet with the actual fillet feature rather than adding it in the sketch, and we're going to add it after we're done modeling other stuff. So we're going to finish this sketch. We're going to extrude this out 1/8 of an inch, because that's the thickness of aluminum we'll use. Typically, air cylinder mounts on Stellar Robotics are 1/8 of an inch, because that's one of the 2 material thicknesses that we use, and that's stronger. 1/16 would not be strong enough. So we're going to set the material to 6061. Once again, because this is a laser cut piece of sheet metal, this will probably actually be 5052. However, the density difference between 5052 and 6061 is not significant enough that I really care. So if you go to the Autodesk material library, they actually have 5052 in there, but I typically just make everything 6061 unless I'm doing stress analysis. If I'm doing stress analysis, then I set the material to be what it should be. But I'm not doing stress analysis on this, so the strength of the material as stored by Inventor is not important. All right, so I'm going to save this. I'm going to just give it the next number, which is going to be 2. Let's go ahead and throw this in assembly real quick. When you're doing fairly complicated assemblies like this, where you're not 100% sure about how all the different things interact, it is helpful to make some different assemblies as you go, rather than doing it all at once at the end. All right, so I'm going to new standard.iam, create, press F6 to go to the home view. I'm going to drag up to place component. We're going to start with our main structural tube. We're going to place that grounded at the origin. This orientation's fine. We're going to right click, place component. Now this needs to be turned 90 degrees, so I'm going to rotate it once by the y-axis. I'm going to place one back there and one in the front. Because it's a flat plate, I don't need to like create mirrored copies or anything. Alright, so I'm going to activate the constraint tool and mate these brackets to the sides of the part like this. Once on the inside of the bracket, once on the side of the tube, and click apply. Next, I'm going to use a flush constraint to line up the backs of the plates to the back of the tube. So I'm going to click on flush, back of the tube, or back of the plate to the back of the tube, click apply, back of the plate, back of the tube, press enter. Then I'm going to do the same thing with the bottom. So bottom of the plate, bottom of the tube, press enter. Oops. Bottom of the plate, bottom of the tube, press enter. Okay, so if I press escape, everything's fully constrained. So we're going to add, like I said, we're going to add holes, we're going to add fillets, we'll round off all these like sharp corners, especially this inside one here, later, but we'll come back to that. So let's save this, not open, save. All right, we're going to give this the next number in the list, assembly 2. All right, so we've got to have a couple brackets here at the front, but we'll get to those in a second. That will hold the pivot point of the mechanism. But let's actually model the mechanism now, just so we have a better understanding of exactly what that looks like, because that's going to bring its own set of challenges with it. So, like I said, I just want a piece of tubing sticking up. The tubing doesn't really represent anything but some structural component of the mechanism that we're going to be rotating. There's not going to be anything to it. It's just going to be there, just representative. So let's just get a piece of, let's just model a piece of 2x1 tubing. Or, I'm sorry, not 2x1, 1x1 tubing. It's like 12 inches long. So I'm actually gonna copy this. I'm gonna go up and do a file, save as. This is our base tube. They're gonna be pretty close to the same. They're both 1x1 tubes. I'm gonna give it the next number in the series, which will be 3. Click save. And the reason I save as like that is because it saves me from having to do the sketch. All I have to do is do a save as, change the extrusion length to the length I want, which in this case is 12, and then save the part again, right? And that's, I have another piece of tube. So it's a lot faster to save as really similar parts and then modify dimensions rather than remodeling the part from scratch. This is also another reason why I'm not adding holes until I'm done with all of the major parts. Not adding mounting holes, I should say. There are other holes that I will add, like pivot points and stuff, such as these, right? I'll add these holes because they're very important, but I'm not going to add mounting holes. Because then I can just save as, and I don't have to like delete mounting holes out and put mounting holes back in. I can just make all the main structural components and then go back in and add their unique holes later. So this represents the arm of the mechanism. It will start straight up and then it will pivot down. So what I want to do is I want this to rotate on a set of bushings. So and we're going to use a 3/8 aluminum standoff as the axle for this mechanism. Now the axle is going to be attached, I'm actually just going to close this. the axle is going to be attached to the brackets that are on the front of this mechanism. They're going to look, the brackets will look kind of similar to this, but there's going to be some slight differences. So those brackets will look, they will hold the axle. The axle will be hard mounted to this, and then the bushings will be attached to the rotating mechanism assembly. So we know we want a 3/8 aluminum rod, so let's go to McMaster Carr here. Let's search for bushings. There we go. Bearings. We're going to use flanged sleeve bearings, oil embedded flange. These are oilite. We know our shaft diameter is going to be 3/8. Just past it. I think we can look at the housing ID, which is the outside diameter of this part of the bushing here. We can go 1/2 inch or we can go larger. We're not doing anything crazy, so we're going to use 1/2 inch. That's a size that we use fairly frequently on Stellar. Now, we don't need them super long, so we're going to go with these 1/4 inch ones, which are kind of really short and stubby. So we're going to click on that part number. We're going to go to product detail. We're going to save a CAD file. Going to show this in folder. Cut this out of here. Don't need that. Don't need my downloads folder. We're going to paste this in here. So now we're going to go back to Inventor. Going to open that file just like we would import any other file. Click OK. Delete the sketch. We're going to set this to bronze cast. It's actually sintered, but that's the closest material. So we're also going to put a work axis down the middle, just like that, and then we're going to give this a save. All right, so that's our bushing. So let's look at this. So we know the outside diameter of this part is 1/2 inch in diameter. It's modeled at 0.501, which is fine. They're modeled to be a little oversized because typically these are supposed to be a press fit. So, you know, this is a 0.501 meant to go into a 0.5 inch hole, so there's a little bit of an interference, which is perfect. So we need to have a 0.5 inch hole at the end of our pivoting mechanism. Now, if we look at this, we said earlier that the wall of this tube is 1/16 of an inch. Right? If we just put a 1/2 inch hole in here and we put that bushing in this hole, and we'll have one on either side, right? So there'll be a bushing here, there'll be a bushing here. The only support that the bushing will have will be the wall of this tubing. Now, most mechanisms, like intakes and stuff, they're going to take quite a bit of load just from the weight of the mechanism, and also they tend to get run into, and there's a lot of vibration. So typically, 1/16 inch is not going to be enough surface area to support this bearing. So what we're going to do is we're going to put a bracket on the outside of this that's going to add 1/8 of an inch. We're going to use 1/8 inch aluminum, and we're going to push the bearing into that bracket and into the wall of the tubing. And most of the load will be taken up by that 1/8 inch bracket, some of it by the wall of the tubing, and then that bracket will be riveted onto this tube. But let's go back and look at our layout sketch for a second. So I'm going to look at this. Actually, before we do that, backtrack here a second. Let's go ahead and, so we're going to need a 1/2 inch hole in the end of a bracket that goes on here, and we're going to need a 1/2 inch hole in the tube. So let's create a sketch on the side of this tube. I press the S key to create a sketch and click. I'm going to project with construction geometry. I'm going to project to the end of this, and then I'm going to create a line. Construction geometry is still turned on, so I'm going to find the center point. I'm going to go in half the width of the tube, so 1/2 inch, which will kind of neatly center the hole off the end of the tube. I'm going to place a center point. I'm going to finish the sketch. I'm going to click the hole feature, and this is going to be 0.5, and termination will be through all. And that's great. Okay, so this will act as the hole that the bushing goes into for the pivot point of this mechanism. So next we're going to have a bracket on top of this, but let's look at that for a second. So if I look at this from the side and I rotate this, all right, let's kind of pretend that this is what this looks like in the up position, right? We want it to be vertical. So if we switch back to our layout sketch, I'm done with that for now. Just save. So this will be vertical. This circle here will be right here, right? So that part's going to be vertical. Now we need to just attach this end point of the air cylinder needs to attach to this part. Now you might be thinking that we have to have like an angled bracket that attaches to this point and attaches to the pivot point. But that's not actually the case, right? Because if we have this piece of tubing that's vertical like this, and we just attach any rigid bracket, I mean, it could be some weird shape, and then attach to this point, this lever arm here that's a nice straight line is actually just virtual, right? It doesn't actually really have to be a straight line. It could be up and over at a 90 degree. It could be, from the end of the tube angling back, as long as it's rigid. If it's not rigid, obviously it won't work, but if it's a rigid component, we don't have to have a nice angled line at this specific angle. It just needs to connect at this point and this point. So this line here could be something crazy like that, right? I just use my right drag thing to do that. But as long as the two endpoints are the same. So essentially what we can do is we know that we want the tube to be vertical, right? We know where the center point of the pivot is. We know where this point is in relation to this center point. So we can kind of just create a bracket that comes off the side of the tube, right? That just comes off the side of the tube and has a point over here that is this point here, right? So if you can imagine just having a bracket that comes off straight like that, and there's a point, like a hole in it for that pin. So that's what we're going to do. However, this bracket's going to be fairly close to the end of the tube, and we mentioned earlier that we need a bracket at the end of the tube to support that bushing, and we need some rivets to hold it in place. So what we're going to do is we're going to create this all in one bracket, right? All one bracket. It's going to be, once again, kind of L-shaped. It's going to come out. It's going to support the hole, and it's going to have an L on it that will have the hole for this. So it's going to be all 1/8 inch bracket that will attach to the side of the tube. So let's look at our cylinder model real quick. Yeah, no issues there. So let's create a new part. I'm going to go back to the home view on this. This will be a standard part. All right, so we're going to have a 1/2 inch hole at the end of the part for the bushing. Now we want the end of this part to look a lot like the tube. So we're gonna make kind of a end of a rectangle here. We know that this hole is centered vertically in the tube, so we're going to use a horizontal constraint to click the center of this hole and the center line of this end line here. All right, so now we're constrained so that we're kind of centered in the bracket here. We know that this bracket will be the same height as the tube, so it'll be 1 inch tall. We also know that that hole, the center line of that, or center point of that hole, is 1/2 inch in from the end of the tube, and we want the bracket to end at the same place that the tube does. All right, so now we know that this is kind of rotated 90 degrees from the way I was just showing you, but we know that coming off the side of the tube, or if the tube is laying this way, coming off the side of the tube, we're going to have another hole for a pin. And remember, before we made it 0.255, because the pin in that clevis is the same diameter as the pin at the back of the cylinder, and that's pretty common that the pins at either end of the cylinder are the same size. So we're going to use 0.255 inches again for that pinhole size. Now we need to finish this structure, right? We know it's going to look fairly L-shaped, so we know that it's going to be flat on the bottom. It's going to come up, could come up at an angle. It could do a variety of things. So and really in this regard, once again, you've just got to satisfy yourself that it's going to be strong enough. Sometimes you can do that intuitively. Sometimes you do have to do a little bit of analysis. Sometimes you just have to over-design stuff as long as it's not too heavy. So we do know that there's going to be some side load on this. There's going to be some load in this direction, not just in this direction on this pin. So I would like a little bit of an angle on either side of this hole just to guarantee strength, but I don't want a lot of angle. So let's create an arc, because the top of this can be nice and round, right? There's no reason for it to be square. So let's create an arc like that, and let's dimension this arc to be, I don't know, half an inch. That's fine. It's maybe a little big. Let's do, that's too small. We'll do 3/8. That's 3/8 of an inch. So that's fine. Okay, so we can connect a line from here to here, and then we're going to need a, if we move this, we can see that this is a sharp corner, which is not what we want. Let's create a tangent constraint here to smooth that out, and we'll figure out what this angle is a little later. Next, we want the end of this bracket to be square right here. We don't want an angle, because we're going to have some holes, and it's nice to have kind of a nice square surface to measure from when assembling. So let's run this up, and then we'll place our angled line. Let's create a tangent constraint here. Now this corner here can still move up and down. Let's create a construction line from here to here and place a horizontal constraint on it. So now this corner is even with this. So you can see we've kind of got like a base rectangle here, and then we've kind of got this little like tombstone shaped thing coming off of it. Okay, and like I said, this is just, I mean, kind of off the cuff. This is what looks about right. This is going to vary team to team. This is going to vary person to person depending on who's CADing it. It's important to be somewhat consistent, but in an FRC environment, it really is just, it ends up being a judgment call. You know, if this was an airplane or something we were designing, we would put a lot more effort into deciding, into making sure that this bracket was as light as it could be while still being strong enough. But in our particular case, we just have to satisfy ourselves that it's going to be strong enough, and kind of do this more based on intuition, which is arguably more difficult at times, but it works pretty well for what we're doing. So I don't think we want any kind of this shape. I think we want this to be centered in this area. So we've got this nifty line here. We can use the center point of this line to line this hole up. So I'm just going to use a vertical constraint to constrain the center point of this circle to the center point of this line. So now we can see that it's like kind of in the middle always, no matter where we move this. So now obviously you can see that this can move around, which is somewhat of a problem. We know that it should be at some fixed location. So let's figure out what that is. So we're going to go back to our layout sketch. And we know, remember, this is laying down, right? So the tube is laying down like this, and actually in the way it'll be in the layout sketch will be like this. So when it's up, right, when the part is up in the retracted position, this will look like this. And in reality, it's probably going to look more like that, just based on looking at the layout sketch. So we know that this is the center point of the pivot, which is this here. And we know that this is the center point of the pin, which is this here. So we can look at, by using the measure tool, we can measure the distance between here and here. And then if we go into where it says delta, it'll tell us the change, the vertical distance and the horizontal distance. So we can see here, it tells us X and Y using the X and Y axis. We can see it's in the X direction, which is the horizontal direction, it'll be 2.251, and in the Y direction, it'll be 1.713. Now, I'm not going to try to remember these. I'm going to open a copy of Notepad, and I'm going to type these in. So X will be 2.251, Y will be 1.713. Yes. Okay, so we're going to escape out of that and go back to our part. We're going to place a dimension. Now, when you're dimensioning between 2 points, the default dimension mode is going to be horizontal and vertical, right? It's not going to be an angled dimension in between the 2 points, which in this case, this is exactly what we want. We want to dimension the vertical distance between the two center points and the horizontal distance. So the horizontal distance was 2.251, I believe, 2.251, yep. And the vertical distance is 1.713. We'll fix that here in a second. Okay, I'm just going to escape out of the dimension tool, and I'm going to go back and measure these again just to satisfy myself that they are correct. They are correct. Okay, so now we need to make this look a little nicer. So let's drag this. We can drag this down, and that's pretty much the only change that we can make. So let's dimension the length of this. Now the other bracket we use 3 inches. I would say that's good here as well. So let's use 3 inches for that. Actually, let's go 3.5 because this is we're not gonna be able to have a rivet right here at the end because of the bushing. So let's give ourselves a little extra length. We're gonna lighten this out, make this a little bit nicer looking, but we'll worry about that later. So let's finish that sketch. Let's extrude this out 1/8 of an inch and click OK. Set the material to be aluminum. Give this a save. Give it the next number in the series, which will be 4. And now we're going to create an assembly with these plates and the bushings. So I'm going to go create new standard.iam, create F6 to go to the home view, place component. All right, so we're going to start with our base tube here. Place that grounded at origin. This orientation's fine. This is the same orientation everything else is in. Press escape. Place component. So we're going to do kind of the same thing we did before. We're going to rotate these to be the right direction. We're going to place one for the back side and one for the front side. Press escape. So now we're going to press, I'm using C, the C key, to go to the constrain tool. So I'm pressing C to go to constrain. And then I'm going to click on the inside of this plate and the outside of the tube to mate those two together. Hit apply. Inside of this plate, outside of the tube, apply. Now I'm going to flush the ends like we did on the other plates, pressing enter after each constraint. I'm going to flush the bottoms, pressing enter after each constraint. And so that'll be that. And you can see the holes line up nicely, which is what we want. So now we're going to put the bushings in these holes. So let's place component. We'll grab this bushing model. Now we need to rotate it. We'll rotate it once by the z-axis. Okay, so that flange will keep it from falling inside the hole. Right? We'll provide a nice support there. Let's rotate it. Oops. I'm going to use Control-Z to undo that. I screwed that up. So Z, and we'll rotate twice by the x-axis to flip it around because we want it. We want one in either direction to go on either side. So let's constrain. You press the C key to constrain, or click the button. Let's constrain this to the inside of the hole. Same thing here on the other side, pressing enter after each one. Then we need to constrain the inside of the flange to be on the outside of this plate. So we'll constrain. We're going to use a mate constraint once again. On the outside of the plate, click apply. Inside of the flange to the outside of the plate, click apply. All right, so that is that, right? So that's pretty much what this is pretty much the entirety of the mechanism. We're not going to go into any more detail here except the detail of these plates and like mounting holes and stuff. But there's nothing else mounted to this. On a real robot, there would be some other mechanism on this thing. So let's give this a save, and we'll give it the next number in the assembly series, which will be assembly 3. We're done with that for now. We're done with that for now. All right, so now we need mounting brackets here. Right, it's going to look kind of similar to this, except we're going to have basically, there's going to be a standoff that goes through here. A 3/8 aluminum rod tapped at either end, and basically, if we look at this and use this as an example, the standoff will go between these, and a screw will go in each of the holes and hold the standoff in place. So the standoff will basically be part of the structure, and then you would slide the standoff through here, and then you would drop it in between the two plates that are going to be up here at the front, and then you would put the screws in to hold it in. If that doesn't make sense, it will make sense here shortly once we put the assembly together. So here's the problem. Okay, if we look at this and we measure the distance from here to here, it's 1 3/8 of an inch. Now, obviously, that makes sense. This is wider than this tube, right? Because this tube and this tube are the same width, right? So it makes sense that we're putting brackets and we're putting bushings on the outside of this tube. It's going to be wider than this tube. So we obviously cannot do what we did here, right? Because the distance between these two brackets is the same as the width of the tube, which should make sense to you, right? I mean, they're placed on the outside of the tube, so the distance between the insides of the brackets is the same as the thickness of the tube, which is 1 inch in this case. So we kind of need more width than this, right? So what we really need is we need the bracket to attach to the side of the tube, and then we need it to come up, and we need it to kind of bend out, and then it needs to be square. It needs to be like parallel at the point at which the standoff for this pivot mounts. So that it needs to come up, it needs to come out a little bit, and it needs to come up again to provide a mounting surface for the standoff. So we've got to do a little bit of sheet metal work here because that's going to be a piece of metal that's bent. So we're going to create a new sheet metal part, and we're going to figure out exactly how much that bracket needs to bend out before it straightens out. So we're going to use a lofted flange. So let's draw a couple lines here. So we're going to start here. We're going to come up. We're going to angle out, and we're going to go up. And this will be kind of one on one side, one on the other. We'll make sure we model the part so it's a mirror image of itself so that we don't have to create two different parts. There's easier ways to create two different parts, but in this case there's no reason to do that, so we're not going to bother. So yes, so nope, I want it back here. So we measured this before, 1 3/8, so 1.375. Now we know that half of that, well, no, let's measure it this way. This will make a little more sense. So from here, from the surface of the tube to the outside of the bushing is 0.188. This is actually 0.1875. It's 3/16, which makes sense because this is an 1/8, and the flange of this bushing happens to be a 1/16, which is pretty typical for bushings of this size. So if this here, right, if our tube is here, right, and this is the, I guess, inside of the bracket, right? So if we look at this assembly here, right, we're really looking at it from this direction. And that bracket is here on the side of the tube. It comes up and bends out and then comes back up again. That's what this is. And this is the inside, this is the inside face of that bracket. And the sheet metal thickness will be on this side. If you remember the class about lofted flange, this will make more sense to you. So we know the distance from here to here needs to be the distance from the side of a 1x1 piece of tubing to the outside of the bushing, right? That's how much distance we need to be able to clear this. So that's 3/8 of an inch, or 3/16 of an inch, I'm sorry. So we're going to dimension from here to here, and we're going to make this 0.1875, which is 3/16. Okay. Now we know that. Oops, that's not what I want to do. All right, we know that we're going to have a piece of 1x1 tubing, and we need a 1-inch surface to be able to rivet to the side of this tubing here. So we know that this part here that's against the tube needs to be at least 1 inch tall. It doesn't need to be more than 1 inch, but it needs to be at least 1 inch tall. So let's just dimension this to be 1 inch tall. Okay, so in addition to that, we're going to have a center point up here where the hole is. Now we're looking at the part from the end, so we can't use a hole. We're just going to use a point that's going to represent the center point of where the hole is going to be running in this direction for the pivot point of the standoff. So we need to dimension the distance from the end point of this line to the hole, which excuse me, will represent the radius of the arc at the top of this bracket. So much like these brackets, right, where there's an arc at the top, there's going to be an arc at the top of this bracket as well. It's just we can't see it in this orientation. So we'll get to that here in a second. But let's use the same radius as we did on this part here, which is 3/8 of an inch. We'll make it the same. So there's that. So, all right, so now we know the distance from, so if this point here is flush with the top of the tube, which is what we've done by putting in this 1 inch dimension, this will be flush with the bottom of the tube. This corner here will be right at the top of the tube. This here will be the center point. So we know the distance from the center point of the pivot to the top of the tube. We know that in our layout sketch, which that's going to be this number here, 1.5 inches. So we're going to dimension that. So we're going to dimension from this point to this corner, 1.5 inches. Now we need to figure out what the angle of this like little jog bend is. This is a little, well, first of all, it could be a variety of things. It doesn't have to be anything super specific. However, we do know that we're going to have a corner. Oops, not this part. This part. We're going to have this corner in here, and this is going to need This is going to need to be able to swing. As this part swings down, it's going to need to be able to swing around, and these corners are going to need to be able to clear. So we can't have this up super. Oops, I don't know what I hit on my keyboard, but I hit something. We know that this can't be super high, otherwise it will still get in the way of the bushing and the bracket and all that. So it needs to be fairly low. However, it can't be something like this, because this puts those two bends way too close together, and we'd never be able to bend it on a press brake. So I know, just based on the tooling that Stellar Robotics uses, that the center lines of these bends need to be at least 3/4 of an inch away for this material thickness in order to have them clear with the press brake tooling that we use. So what I'm going to do is I'm going to use the dimension tool. I'm going to click on this line. Now, right now it wants to give us the vertical dimension of this line or the horizontal dimension of this line. What I want is the length of this line. So what I'm going to do is I'm going to right click, I'm going to click aligned, and now the dimension is aligned to the length of the line. I'm going to make this 0.75 inches long. I'm going to call that good for now. That should be manufacturable using the equipment that we have. And we should be ready to perform our lofted flange. So let's finish this sketch real quick, and let's talk about the width of this bracket. So here we've been using 3 inches. We know that here we have 1 inch. Oops. We have 1 inch on the outside of this pivot. So we've got 1 inch here. If we make the bracket, in order to make the bracket symmetrical, we can make this bracket 2 inches wide. Now that will give us the 3 holes that we need. And you'll see once we start putting together. So like I said before, you need at least 3 holes in the bracket. Now, because this is pivoting, there may or may not be large amounts of load on this bracket, depending on exactly what you're pivoting and how likely it is to get run into by other robots or something like that. For this example, just to save us some time, I'm going to just create the bracket so that it's a mirror image. If you needed more strength, you'd have to make the bracket longer in this dimension, because you can't make it past the end of the tube in this direction. I mean, obviously you can make the tube longer, but if you're constrained for space on your actual robot, you couldn't do that. So you'd have to make your bracket look more like this, kind of L-shaped like we've been doing. But that means that with this weird offset, there's going to be a left hand and a right hand version of the part, which gets a little more complicated, and we're not going to go into in this project. Okay, so what we need to do is we're gonna create. We've got an inch on this side of the bracket that we can use, and we're going to use an inch on the other side of the bracket as well. So we're going to make it 2 inches wide, which means we need to create an offset version of the sketch 2 inches off the front in order to perform our lofted flange operation. So we're going to click plane, we're going to click the XY plane, we're going to drag this out, we're going to type in 2, we're going to click the green check mark, then we're going to start 2D sketch on the plane we just created. We're going to use project geometry. We're going to click these 3 lines that we've created, so we have a copy. We're going to finish that sketch, turn off the visibility of this plane because it just kind of gets in the way. Close that. Okay, now we're going to click lofted flange. We're going to click on the first sketch, then we're going to click on the second sketch. Okay. Now, you notice what I said before. These are our lines right here, the green, the very, very light green that we can't really see very well, but it's there. This here is our sketch. Now, I said before that we want the sheet metal to be on this side. So what we're going to do is we're going to use offset direction. We're going to flip it to the other side. This is what we want. We'll change the thickness. This is close, but we need to make it 1/8 of an inch. So this looks about right. You can see there's not actually a sharp corner here, obviously, because it's a bend. It's very slight, but that's fine. That doesn't hurt anything. Same thing here. It's a radius, but that doesn't hurt anything. It goes to the end, which is great. Let's change our bend radius to be 1/4 of an inch. I don't actually know off the top of my head what it is, and for really slight bends like this, it's not particularly important. In the bend theory portion of the CAD class, and when we were talking about sheet metal, I emphasized making sure that we get the bend radius right. But with bends that are, I would say, less than 30 degrees, that's not as critical. And for material like this, modeling the bend radius is something large, like 1/4 of an inch, is typically sufficient. So that's as good as I can get. I don't actually know what the exact bend radius would be for this exact bend angle. So click OK. Let's go to sheet metal defaults, uncheck use thickness from rule, and change this to 0.125. You can see it was already fairly close, but that's just Inventor's default. Click OK. You can see it got a little thicker. Set the material to aluminum. Okay, so now you can see this is rectangular. We were talking about having a nice arc up here, right? We wanted a nice arc. Well, why don't we have a nice arc? Well, we have to make a nice arc, okay? But we have to do this a little differently than we've done it before, because we're kind of we modeled it in this direction, but now we want a fancy shape in this direction. So what we're going to have to actually do is we're actually going to have to cut material. We're going to have to model. We're going to have to draw that shape in a sketch and then cut the material away to make the shape that we want. So let's start by creating a sketch on. This is the inside surface. Let's create a sketch here. And then we're actually going to place our hole up here. You could have created a sketch on this surface, but it just feels more consistent to me to do it on this surface and then just use through all to make sure the hole goes all the way through. All right, so I'm going to project the top line of this using construction geometry. Then I'm going to draw a line from the hole to the center point of that projected line. Then I'm going to use a vertical constraint on that line. Now we know that we want the hole to be 3/8 of an inch from the top of the bracket, so that we dimension that like that. Then we finish the sketch, click hole. Now remember, this is going to be a mounting hole for a standoff. So basically this is a screw hole. A screw is going to come through here and the standoff is going to mount to this inside face. So we're going to use a number 10 screw, a lot like we did on the gearbox. So we're going to click clearance hole, and we're going to wait a million years for that to load, because it does that the first time you use one of these other special types of holes. So we're going to go down under size to go to number 10. Our termination's through all, so click OK. All right, that's perfect. All right, so now we want to cut out our shape with an arc that's concentric to this circle. So let's create a sketch. Press the S key, click on this face. You can press the S key or you can click this button up here. So let's turn on construction geometry. Let's project that. And let's project the bottom and the top. This is a little bit of a complicated sketch, and I'll try to explain exactly what I'm doing to the best of my ability. So I turned off construction geometry. Let's start with the arc. Okay, and this is not like any, there's no dimensions to this yet, but we'll get there. Okay, so now we need construction lines up from these bottom corners an inch. And you can see these are kind of like in the middle. The end point of this line is kind of in the middle of this bend, which is what we want, right? Because this bend represents actually a sharp corner that ends right at the edge of the tube. So that's the reason why I'm creating these lines, is because we need to know this line and this line are not in any particularly significant location. So we're using these 1-inch lines to be able to locate where the top of the tube is. So this dotted line here represents the top of the tube. Actually, we could delete this dimension and place a horizontal constraint on that line. So this is the top of the tube. So we want this part to be square, and we want to start angling from the top of the tube. So we're going to draw a line. We're going to turn off construction geometry from here to the arc, and from here to here. Now you saw on this first line, it automatically placed a tangent constraint here, which is kind of nice because that's what we wanted, but it did not place a tangent constraint here. So we're going to do that manually. So click tangent constraint, click on the arc, click on the line. Okay. So now we know that we want this arc to be touching the top of the bracket. So let's pick the tangent constraint there, click the arc, and click this top dotted line. All right, so now we're not cutting out this region. We're cutting out this region and this region. So we've got to kind of box this outside region in order to be able to use the cut feature to actually cut that. So let's grab our line, make sure construction geometry is off. We're going to start here at the corner. We're going to go up to the top corner of this, place a line there. We're going to do the same on the other side. Now, from here, we're going to go to the midpoint of this arc. Now, you can see I've got two different states. I've got this green dot, which is actually, when you see the green dot, it's actually placing it to the midpoint of this dotted line, which is not exactly what I want. If you see this little like yellow X, if I can get it, there we go. You get this little yellow X, you got to just hunt around for it with your mouse. That's going to be the intersection between the arc and the dotted line at the top of the bracket. That's what I want. So I'm going to click, then I'm going to do the same thing here. And I'm just going to attach it to the, and then now it's attached to the end point of this line, and I got a tangent constraint, that's fine. So now, if I try to finish this sketch and go to the cut tool, it works just fine. Okay, so I guess we're done. Sometimes, I'm just going to show you guys anyways, sometimes Inventor, if you're not careful, maybe if you place it to this midpoint of this line, or you're just not careful, and sometimes Inventor will not like this. It won't recognize this as a closed region. And what you actually have to do is you have to split this arc into two pieces. And you can use that using the split tool. So you see this little X. If I hover over this, you see the little X. That shows that it'll split this arc into two pieces. Now, I'm not going to do it just because that'll make this sketch a little more messy. And there's no reason to do that because Inventor's happy with the way I did it. But if you're doing this on your own and you're having trouble with it, and when you get to the cut tool, it's not showing these as green like it is here, and you see how I can hover over these and it'll show me these two regions. If it's not doing that for you, you'll have to use the split tool and in the sketch and click on this arc to split it into two pieces. So that's just a word of advice. So I'm going to click both of these. My extents distance will be all. Now because we're actually going to be cutting part of this bend here, I'm going to click cut normal to make sure that this maintains a perpendicular surface in the flat pattern. We talked about what that means exactly in 2 weeks ago in the CAD class. So click OK. And now we've got this kind of like nifty looking part that's got an offset on it. So once again, we'll put holes and all that stuff in a little later. Let's go ahead and save this, give it the next number in the series, which will be 5. Now we're going to come back, not that one, this one, and we're going to constrain it in here. So I'm going to place component, grab this one, place one on this side. Now I actually have to rotate this around for the other side, so I'm going to rotate by the y-axis twice. Now, same exact constraint scheme is over here. Mate the interfaces together like that, and the interface to the outer face of the tube like that, and then flush the ends to the tube like so. Flush to the end of the tube, then flush to the bottom like that. I'm pressing enter after each one once again, just so I can go fast. Okay, so this is our finished. I'm going to give this a save. This is like our finished base assembly. So the back of the cylinder will attach with a pin, probably a bolt, back through here. There will be a standoff through here that will provide an axle for these bushings on this pivoting component here. And then the air cylinder will kind of connect everything up. So next video, we're going to model the standoff in here. We're gonna start putting holes in everything. We're gonna put all of this together in assembly, and then probably a fourth video we'll add the fasteners and whatnot. Thank you for watching. We will continue this in the next one.